Hello, my name is Chip. I'm a co-founder of Claypot AI, and I also teach machine learning systems design at Stanford. Snorkel is one of my favorite companies, so I'm really excited to be here today. Thank you so much for having me. I'm going to talk about platform for real-time machine learning, and I want to start with a little story. So recently, I went to an e-commerce website to look for a work from home setup. So I started looking into monitor, keyboard, setting desk, mouse, and I kept hoping that the website would be able to understand what I'm looking for and just tell me, hey, this is a great product that suits your need, just buy it. However, after 15 minutes, the site was still trying to sell me mattresses. So I left the site because I was like, I can't find anything I want here. My experience was not unique. In the survey that my friend shared with me, like 40% of shoppers said they would leave a site if they are shown irrelevant recommendations. And so you might wonder, so what if we just look at like a user's historical data to generate recommendations relevant to them? And that's how a lot of companies are doing things nowadays. But that's not sufficient. So most users are not logged in or are not logged in frequently enough for a site to have sufficient historical data. So, for example, like 70% of shoppers only logged into a site once or twice a year. So, which means that to be able to generate relevant recommendations, we have to look into like each user most recent activity or like in-session activity to generate recommendations. So real-time machine learning is an approach to enable machine learning models to leverage freshest data to make most relevant predictions and also to update itself or like retrain itself to adapt to changing data distributions. And that's the topics that we're going to talk about today. So we're going to cover three topics. First, online predictions, and then continual learning, and then real-time monitoring, which is like extremely important to enable continual learning. So online predictions. So online prediction is as opposed to batch predictions. Batch predictions refer to when predictions are computed periodically, like before requests arrive. For example, on Netflix, they might look at owned users and generate movies that each users might want to see next, like every 4 hours. Whereas online predictions means that predictions are computed on demand after requests arrive. So instead of like generating recommendations beforehand and cache those predictions and I show the prediction to users when they log in, you just wait for users to like log into the website first and visit the website first and then look at their recent activities and make recommendations. So batch predictions is a way to like avoid latency because you generate predictions beforehand, so you don't have to worry about how long the predictions are gonna take. However, online prediction has like strict latency requirements because you don't want to like users to wait forever to see like recommendations or like other activities. However, batch predictions might mean a lot of wasteful compute. First of all, on Grubhub, like only 2% of their users actually order like a day, but they have to like generate recommendations for restaurant recommendation for own users every day, which means that 98% of predictions actually not used. Online predictions allow us to make more adaptive and more relevant or like useful predictions because we make sure we really generate predictions when users actually need the predictions. So from the architectural perspective, batch prediction looks something like this. So we first generate predictions and we store it to like data warehouse. And then you might want to load into some key value store like DB or Redis for like faster retrieval during faster retrieval. And when you receive a prediction request from the apps, then you fetch the pre-computed predictions. And it goes for a lot of use cases, for example, like churn predictions or like predicting users' lifetime value or risk planning. So you don't really need to do online predictions for those use cases. So another setup is online predictions with batch features. So in this case, predictions are made online, but using features pre-computed. So for example, like for recommender systems, you might want to like pre-compute on the product embeddings. And you first generate on the embeddings and you also load them into a key value store for faster retrieval. And then when you look at when a user visits a site, you look at all the products that users has looked at recently, and then you fetch the embeddings relevant corresponding to this product, and then you use those pre-computed embeddings to make predictions on what items user want to use next. And it's an extremely common setup. Another setup which is more advanced is when you do online predictions, but not just with pre-computed features, but also like features that are computed on demand. So for example, like to make more relevant recommendations for the product, you might want to use not just the products, not just using the product embeddings, but also like other product features, like how many views a product has been looked at in the last 10 minutes or like 30 minutes, because maybe there's gonna be some trend and suddenly the product is like really popular and like a lot of people want to see them. So you might want to show this, like the trendy product as well. So the view, like how many views a product has in the last 30 minutes is an online feature that can be computed online. So for this use case, a lot of use cases can benefit from online predictions with online features and batch features. For example, dynamic pricings, estimate time of arrival predictions, or like trending products. So when we do online predictions with online features, so a problem emerges, which is a train predict inconsistency. So during training, we might want all the features are computed in batch, like using in batch process from historical data using some batch processing like Pandas, DAS, Spark. Whereas when we do online predictions, these features, online features are computed online, perhaps through like a stream processing process like KSQL Flink. So now here's the inconsistency. So like training features are computed in batch, but they predict features are computed like using stream processing. And this problem has got a lot of headache. So there are like various ways to like go about it, but one way that we've seen a lot of companies adopt very successfully is to leverage stream processing as a base. So what that means is that like when we write feature definitions, instead of writing it in Python, we write the feature for online prediction process. So we write in a SQL definitions, and then during predictions we can just like use stream SQL to like compute these like SQL features. And if we want to generate data for training, we can apply this same feature definitions, but like apply it through a backfill process so that we can generate, so we can compute these features for historical data. And that way we can ensure consistency between train and predict. And it's a very common approach, like for feature stores, such as like feature form, Tecton. Okay, so we talk about like predictions, now we talk about continual learning. So deploying a model is easy if you ignore all the hard part, and that's a quote we got from a friend at Square. So a lot of industries today, we are still doing easy deployments. So easy deployments means that we look at deployment as a static one-off process. So we have a new model, we do some ad hoc offline evaluations, and we package the model, and then we ship that model to production service. So it's easy, not because, so it's easy, people do it not because it's the right thing to do, but because it's easy, and it's easy now, but it's gonna be very difficult later, because like when we ship a model to production service, and then what? Like if a model fails, we have no idea. We have a lot of use cases. We have seen a lot of cases where the model fails for weeks and nobody figure out until somebody decided to like dive into like the predictions output. And if you want, there's no way to close the loop, the model update process becomes very ad hoc and painful and require many people involved. For example, like one person needs to go into data warehouse, different data sources to like generate data, and then do apply data engineering, and then generate feature, train model, and then hand it to another team to deploy. So that's why we see that a lot of companies, they really update the model like once every 6 months or once every year. And after a year, that the world has changed a lot, and the model is no longer very useful. So we are pushing toward what is called like hard deployment, or like seeing deployment as a continual process, like never-ending process. So we have some more update. You do some like offline tests, and then you can package model, ship it to prediction service. And we see that prediction service has to be very much tightly coupled with online experimentations. We see in many companies, they have an online experimentation platform separate from the prediction service. And what that means is that it's make it very hard to the scientists to like schedule like shadow deployments or A/B experiment. And and it's like really hard to switch book at them and I see the result or like end experiment at will, or like schedule a new one. So actually deploy a model. Imagine that you have done all the necessary online experiment, and then you need to monitor the model. You need to like have some set of like alert triggers so that we can trigger the retraining. And the training service would need to figure out a way to like gather data either from prediction service and joining with labels, or like from other sources. And then the new updated model will go through the same exact process again. So people think of continual learning as something just like means that we have to update the model every 5 minutes or every 10 minutes, which is not really the case. So continual learning just means that like we have a way to automate the model retraining. We can do it on demand and we can do it like stateful or stateless. So here we break it down into like 4 stages of continual learning. So the first stage is just like manual ad hoc retraining. So like maybe like whenever someone has free time, which can be like never, you look into you get the data and you retrain model and then you manually push the new model. So the next stage is just like you want to have some like kind of like automated cadence-based training. So you might want to set up, you might want to write a script to automatically fetch data, compute features, retrain the model, like maybe like once every day or once every week. And this process is really like stateless retraining, which means that the model is trained from scratch each time. So the next stage is like when you do the same automated cadence-based retraining, but then you can do stateful training. So instead of training the model from scratch each time, we train the model from the last checkpoint. So that like, for example, if you want to train the model every week, instead of training on the whole data from the last 3 months or the last 6 months, we only continue training the previous model on data from the last week. So stateful training is like quite neat. So experimentally, we have seen that a lot of companies get like can reduce a lot of like training time because instead of training on data from the last 6 months, we really have to train data from the last week. So the training process is shorter. And also somehow the model converges faster and like with better accuracy. And so the last stage for continual learning is like instead of having a cadence base every week or every month or every day, we can have the on-demand retraining. So whenever there's a trigger for model retraining, we retrain the model. So for example, like suddenly we detect some distribution shift, then we trigger model retraining using latest data. Or like whenever we realize that model performance is low or some sort of trigger like all the predictions request return 0 for somehow, then we also trigger. So that is on demand. So automated on demand stateful training is what we refer to as continual learning. So there are different smart way to trigger retraining. So the simplest one is just like manual trigger or like cadence-based trigger. But there are more sophisticated triggers, for example, volume-based. So we work with like a lot of B2B companies, and for B2B companies, they work with multiple customers or clients, and each customers or clients has their own model and their own data. So they don't want to like, and some customers have like, more traffic than other, so they don't want to retrain own models or own customers as the same cadence. So they want to say, oh, whenever a customer has data existing in certain threshold, retrain. Or like performance based, also drift based. Drift based is like extremely hard to do. So there are 3 challenges to continual learning or continual deployment. So we're gonna go through each of them. So the first is a fresh data challenge. Like to be able to continually train the model on fresh data. So we need to access fresh data. So which means that we require to like pull data from multiple data sources. So you might have like some data in data warehouse, you might have some data in real-time transport, you might have like third-party data. And for a lot of companies, like the process of like gathering, or that I have seen, so the process of gathering data from multiple data sources is really the most time-consuming part. And then of course, if you do like supervised learning, right, we would need to have like labels for the model. So in some use cases, we have like natural labels. So for example, like ETA or ETA or recommended systems or SCDR click-through, then we have real natural labels. For example, for recommended system, we know it's like maybe we assume that if the user clicks on a recommendation, then it's a good recommendation. If they don't click on a recommendation, then it's not. So that's sort of that kind of give us like the labels, so we can extract labels from the click stream. But for many use cases, we need to annotate the model, the data. So that is when like solutions like Snorkels comes in really handy, because Snorkel allows us to like to generate labels for us on new data very fast. And then of course we have to join these labels with features of the new model, of the new if we have new features, so that we can generate new training data. So another challenge is the algorithm challenge. So a lot of models can be updated using just like a small set of data. For example, neural network, you can just like update a neural network with just one sample or a 10 sample or like 100 sample, and it works. However, for models like matrix-based model, for that to work, you will first need to like construct the entire matrix of from the owns of data, and have to do like and then you might want to apply some like dimension adder reduction techniques. And that's the process is very costly. You can't do very frequently. So you might want to construct the full matrix first before performing like dimension reductions. However, I think I have seen quite some interesting research that enable matrix-based and tree-based models to be able to like incrementally learn. So another challenge, which is like really difficult one, is the evaluation challenge. So the more often we update a model, the more chances that model has to fail. So we need to, if we want to update the model fast, we need to go to like to go to evaluate that model update fast. So which brings us to the next topic, monitoring. So there's a world of difference between real-time monitoring and batch monitoring. And I see that a lot of monitoring solutions tend to conflict the two, especially the batch monitoring solutions one. So batch monitoring solution means that you probably compute your metrics, like what are the metrics you care about, like accuracy, distributions, label distributions from some historical data. So you might need to wait for the data to like be dumped into the warehouse first, and then you run a script to like compute this metrics maybe like once a day. So that means that if we deploy the model today, you have to wait until the next batch of metrics is computed to even like get some sense of like how the new model is doing. Real-time monitoring in contrast continually compute metrics from the data stream. So you might have like using like something like Kafka or Kinesis to like transport the continuous click stream from the applications, and then you just using a stream processing engine just like continually compute like accuracy or predictions, so that like as soon as a model is deployed, as soon as there's traffic coming in, it will be able to like see how the model is performing. So when we talk about monitoring, you might wonder like what to monitor. So what business really care about is business metrics like accuracy or click-through rate or like purchase-through rate, or like the percentage of like frauds being detected. However, like this is not always possible, because to be able to like compute these metrics, we usually need to have user feedback or label. So a solution is that you might want to like collect as much user feedback as possible. So you probably saw recently about Netflix. They introduced a double thumb up icons. So I'm not quite sure why they did it, but I would imagine that it's probably this kind of double thumb up feedback allows the recommender systems to generate more relevant content to users. So like for an e-commerce website, you might want to look at like everything like from click, favorite, add to cart, purchase, return, and different kind of like user feedback has different implications. For example, clicks is very abundant. Like users might click on a lot of things, but they have very weak signals. So like clicking on something doesn't mean that like users will like it. Whereas buying and purchase is a lot less available. So users might buy an item very rarely, but then it's a lot stronger signal. So some companies, they optimize for click-through rate, some optimize for purchase through rate, and what kind of feedback works best for you really depends on the use case. So another solution is you might want to like leverage solutions like with supervisions, like Snorkel, or like active learning, so that you can generate labels for the data faster. So when we don't have business metrics, companies look into predictions and features monitoring. So with the assumption that like shift in predictions and feature distributions lead to a decrease in business metrics. So in that scenario, monitoring becomes a distribution shift detection problem. So how to determine that two distributions are different? So first we need to like to detect distribution shift, we need to know like what is our source distribution and what is our target distribution. So that if the target distribution is different from the source distribution, then we say that there's distribution shift. For this, the what was a very difficult type of shift to detect or the temporal shift is like when data changes over time. And for this, like time window scale really matters a lot. For example, imagine we have a distribution like this. And imagine that if we want to like today is a day 15 and we want to see whether day 15 there was some distribution shift. So if we use day 9 to day 14 as a source distribution, then we say that, oh, day 15 is very different from day 9 to day 14. So this is pretty a shift. However, if you use day 1 to day 14 as a source distribution, then we may see that, oh, the spike on the day 15 actually expected is like very periodical. So this is not a distribution, and this is not a distribution shift. So we talk about like monitoring features or predictions, and a lot of solutions today focus on monitoring features. So to monitor features, usually people like look into changes in feature statistics. So for example, you might look during training, you might generate the means or the variance for a feature, and then you store these means and variance. And during predictions, you also compute the mean and variance of the features, and then we compare these means and variance with the means and variance computed during training. And if they are different, then you say, oh, there's distribution shift. So like the expected like means variance with equal expectations, but they don't have to be like just means and variance. They can be like other expectations. For example, like if we know that's the is the most common word in English and you're doing and NLP, so you want to monitor when it counts the number of the you encounter in production, and if the is no longer the most common word in production, then you might say, oh wait, something is happening. Yeah, so for this kind of monitoring, it's very inconclusive. So because like if we see that, oh, if the mean and variance are different, then we may say that there has been a shift. But like if they are still the same, it's not definite that there is no shift, because there might still be a shift. But like the statistics or the expectations or schemas that we computed as is not sufficient to detect them. And there's also like other problems with monitoring features. The first is like the compute and memory cost. So a company doesn't just have like one model with like 10 features nowadays. So we talk to a lot of companies that have like hundred of models, and each model has like thousands of features. So imagine just like computing like continually computing statistics for like tens or like a hundred of thousands of features can be very, very costly, expensive. And also, it's like when we have so many features, it's very likely just like some of them change from time to time, like a lot. So like if you have 10,000 features, very likely maybe 10 of them change a day. So it's enough to us like having a lot of like alert fatigue, because like most of these changes in features statistics actually are not important, like they actually don't really do anything in the model. So if you skip alerting, like or developer data scientists, every time this change over time, they get sick of on the alert because a lot of them are false alarms. And also like because when you compute statistics, this statistics might change over time. So we need to figure out a way to like manage all these like expectations or these statistics, so we know this like what are the expected statistic for the model, because it might change the features from time to time. So unfortunately, most of monitoring solutions today still more focused on feature monitoring, and so do feature stores, because feature store have compute features. So it's only natural that they also monitor features for you. So if you want to look into monitoring solutions, you might want to look into like whether they do real-time monitoring and batch monitoring. And a very important thing that we have seen that makes a lot of companies not use monitoring solutions is because these solutions don't support custom metrics. So one thing I learned is that like every company cares about different things. Some care about accuracy, some care about precision, some care about top three accuracy, some care about some fancy metric like NDCG or like some diversity metric. So you need so for to look into monitoring solution, we really need to look into like whether that solution can support you ad hoc metrics. So yeah, that is my talk. My time is up. Thank you so much for having me. And here's my email. Here's my Twitter. Please reach out if you have any questions. And also, I just had a book coming out as well. So if you're interested in the topic, please do check it out. Thank you so much and have a nice day.